Hey everyone, thank you so much for joining us for today's hardwear.io webinar. My name is Antriksh and I'm part of the hardwear.io team. We have been running hardwear.io conference and trainings since 2015. The conference also had a successful event last year in the US, and due to the pandemic situation, we have switched to the online mode now. The objective of the conference revolves around key concerns related to hardware, firmware, and related protocols. We are trying to create a continuous learning engagement with our hardware community. Hence, webinars are always interesting to learn and share knowledge. Additionally, we have also started our hardwear.io online trainings, which is going to be scheduled in the month of September. So please feel free to have a look at the links sent to you on the chat. And if you are interested to join, please feel free. We have some amazing trainings lined up for all of you. Today we have Matthieu, who is a software engineer with Quarkslab. He has his interest in cryptography. He's regularly doing research and development with regards to software protection engineering. Matthieu would deliver today a talk on building Whitebox attack and defenses with his colleague Philip and Adrian. A quick announcement. The format of today's webinar would be 30 minutes of presentation by Matthieu and 10 minutes for Q&A. Those who have questions and would like Matthieu to answer them, please type in your questions in the Zoom chat option, and Matthieu would answer them with his team after his presentation. We will also send out feedback links to all of you. So please help us improve our webinars for future. And if you would like to present in our upcoming webinars, that will also let us know about it. So now, Matthieu, the stage is yours. I would stop sharing my screen and it's all
okay.
You.
I guess I will start sharing mine.
Yes.
Is it like going to pick? Okay. It's working, I guess. No?
Perfect.
So, hello. My name is Matthieu Daumas. I've been working on this webinar with Adrien, Guinet, and Philippe. Here at Quarkslab, we have some history doing security audits and now building software protections and whiteboxes. Philippe is known in the Whitebox community to have contributed to several publications on attacks on the IES whiteboxes. And Adrien is our lead tech on these problematics around software protection and whiteboxes. And I've been working with Adrien on defense and Philippe on attacks. So the title of the talk today is like building whiteboxes, attacks, and defense. We have the both sides behind this presentation. So let's start. The content today will start with a quick overview on whiteboxes, like an introduction, and then we'll switch to attacks and defense. We'll start with high-level attacks, then go a bit more into the details, and then we're going to have a quick conclusion, then switch to the questions. I'll be the only one talking during the presentation, but during the question, both Adrien, Philippe, and me will answer the questions. So a quick introduction on whiteboxes. Often whiteboxes are introduced when the problematic is like, please protect my cryptographic implementation. When we say that, what do we mean? Often it's about the keys, the data, and sometimes other kinds of abuse, like more complex scenarios. And what we see here is like when working with whiteboxes, it's important to define our context and also to define our attacker model. The term whiteboxes comes from the attacker model. It's like we work in the worst case in some ways. Our implementation can be read or written by the attacker. It's like a white box, a box that can be opened. And the attacker has full control on the operating system and the hardware. And the attacker has the application runs with the least possible privilege. So what you see here is like, we are really in the worst possible situation in some ways. If you ask yourself, can the attacker do that? Can the attacker change the operating system or do X, do Y? it's often yes. The answer is often yes, the attacker can do that. So in a nutshell, what we are talking about when we say white boxes, often it's like, here we have a regular implementation. IIS gets a key, and then IIS can encrypt something. And when we are going to work with white boxes, often we are like, white box IIS, it's not getting a key. The key is hidden inside the white box. The key is not explicit to the attacker or the people building the application in some ways. And afterwards, the white box can encrypt things. And for example, here, the attacker can't extract the key. We built the white box in a way that this task is hard. And for example, the attacker can't extract the key to decrypt data with the same key, for example. So the general idea about white boxes is we are going to take standard algorithm, ones that already exist, and we are going to build an implementation that is like kind of black box, but white, from which the attacker can't extract the key and can do fancy stuff like changing how the white box is used in the application. And in practice, building such kind of boxes is like kind of hard because theory is not working with us here. So in practice, this is a compromise between mathematics and obfuscation software protections. So what you need to understand from this summary is like, when we build white boxes, when we build this kind of software protection for cryptography, is about making the attacker's work hard enough. It's not about age of the universe hard. It's more about having an attacker pouring tons of resources and tons of knowledge in order to do little things with a white box. And we don't want to be easy to break, but we want to be hard enough. And it's a compromise at the end of the day. So let's start also on how to build a white box, a very high level way of thinking what happens into these magic implementations. For example, here we have a cryptographic function that gets a key, a data, and outputs, for example, a plain text. And we are going to replace this cryptographic function with a table. Here we have the same function, but pre-computed in a large table. And then the input data will index this table and we get the right output. But as we have inside this pre-computed table only the results, it will be really hard for an attacker to extract the key. In this kind of white boxes, the key is really implicit and the attacker has like a lot of difficulty to extract the key. But in practice, we don't do that for large functions. For example, for IS-128, it's like petabytes tables, so it's not very practical. So what we like to do when we are working, for example, with IS, is like we are going to split the algorithm into smaller operations, and we are going to work on intermediary states, internal states. And we are going to have way more practical white boxes here. And what we can do when we work with that is even having the key as a secondary input of some tables, for example, or having the key modifying the tables. And if we protect the key in some ways, we can have a dynamic white box, like an IIS white box from which we can change the key. And here we have a protected key from which we can't extract the key. So there is like compromise and things we can do to play with. So this is how we build white boxes. To sum up this example, we are working often when we work with white boxes with encoded internal states. We tabulate smaller operation to process these states, and this gives a lot of margin to the attacker to change our white box. So often we need to protect our internal operations and how the states are processed with obfuscation and mathematics and things like that. What I want you to understand here is like it's a security size performance compromise, because we've seen like kind of perfect white box with unpractical size like petabytes table, and on the other side there is like the fastest implementation we can find, like OpenSSL is like a very good implementation in terms of size and performance. But the end user wants kind of a trade-off between these two extremes. And a good way to understand why and what is this kind of trade-offs is to take an example with digital right managements. Digital right managements really likes white boxes. And here, for example, in the third line, you see there is some data like a movie, for example, that is encrypted by the server and sent to a client. So when you decrypt a movie with a white box, you need really good performances because the movie is really big. But for example, the several stage on the top, in orange and red, that gets the key to decrypt the movie, for example, only process very few bytes of data. So you can have a strong sense of security here and have a different trade-off, more big white boxes, for example, or white boxes with more countermeasure, more slow. So this was everything I had to say during the introduction. Now you know about what are white boxes, a quick way how to build white boxes, and what are the trade-offs we want to do. And now we are going to switch to attacking and defense on white boxes, and we are going to start with high-level attacks that works on all kind of white boxes, then switch to some algorithm. We are going to start with code lifting. Code lifting is a really nice attack. Imagine you want to steal a movie again. You have a very complex white box that decrypts the media stream. And you are an attacker, but a lazy attacker. And you don't want to understand the content of the white box, but this is like no problem. You put a curtain on your white box and you're like, no, I can still steal the movie because I have some kind of big black box in which there is like some small white box. And from this white black box, I get a decrypted movie. And at the end, you perform the attack, like stealing the movie, but without extracting the key. But do you need the key here? No, you have the movie, so it's fine. And in practice, code lifting is this kind of stuff where we extract useful high-level primitives from the white box. And then we use these primitives as to achieve the desired result. Here, stealing a movie. And in practice, this kind of attacks are often attacks that even with a good quality white box, the attacker, without too much in-depth analysis, can instrument your white box and do things he wants it to do. And the countermeasure here is like when we extract the white box, we want it to be bounded to its environment and the code it's executing in order to, like, when we extract it, it changes its behavior. Often, when you have a white box, you must ask yourself explicitly, is your white box protected against code lifting? Because this kind of protection are not trivial to implement. So if you don't have the feeling of taking action to prevent this kind of attacks, maybe you need to ask yourself, am I protected? And now we'll switch to dataflow in white boxes. It's kind of code lifting on steroids. Often when we whitebox stuff, we have wall protocols we are working with more than one primitives, sometimes digital signatures, key exchanges, complex key derivation processes. These are very common in whitebox schemes. And the example is, again, digital right management. For example, we have here both the server and the client sharing a master key. The master key is used to decrypt and protect a pair client key. And then the pair client key is used to decrypt and protect a pair content key, a pair movie key. And now the movie key is used to decrypt the plain text data. And here the attack an attacker can do is the attacker comes, looks at your white box, see there is like two functions, one that decrypt and protect, for example, IS and other things, and the other one that decrypt the movie, just doing IS and then giving a plain text movie that you can play on TV, for example. And here the attacker will modify the data flow to extract an unprotected copy of the client key, for example, by using the second function instead of the first function in the order of operation, for example. And the solution to that, sometimes code lifting protections help, but these are not only mitigate the problem in some ways. And what you really need to do is like tweaking how each key is unwrapped, how each key is protected, in order to enforce the data flow, enforce the order of operations. And at the end of the day, you must ask yourself a similar question: is my Whitebox data flow properly enforced? Because if it's not properly enforced, you can have a lot of mathematics inside your Whitebox, but it won't be protected against this kind of manipulations from a lazy attacker. And now we are going to switch to IIS Whitebox. The IIS Whitebox is kind of interesting because there is like a long history of literature published on IIS. Whiteboxes has been started with IIS and DES, and now we have, for example, 20 years of people publishing designs of IIS Whiteboxes. And also we have 20 years of people breaking all the designs, and often it's like, let's take a look to the operations we are doing to the table. In the tables, let's take a look to the internal state and then do mathematics in order to extract the key, for example. This kind of attacks often need to first reverse all obfuscation layers to access the underlying design, to access the underlying tables of the Whitebox. Then you need to understand and implement the corresponding academic papers. It's like people published papers about how to break this design, for example, but they didn't publish the tool. And now you need to tweak the attack in order to fit the specificities of your design, of the design of the Whitebox you're attacking. Because often vendors like put their own spices into their Whitebox and do tweaks. So it won't work on the first try. But at the end of the day, you can still do algebraic attacks, mathematical attacks. But these are time consuming, as these are not off the shelf and require a large effort or reverse engineering. So as an attacker, I don't want a hard enough Whitebox that require a lot of reverse engineering, a lot of mathematics. I want a cheaper attack. And can we do cheaper in terms of attacks on IIS? And the answer is yes. And the answer will be often yes on all kinds of Whiteboxes. And the trick here is to inspire yourself from the hardware world. It's like we know how to attack Whiteboxes by observing, for example, the power consumption of a chip. We know how to attack like hardware implementation of IIS by perturbing their behavior, like shooting lasers at IIS computing chips. And from these attacks known in the hardware world, we want to build Whitebox attacks because these have very few assumptions on the targets. It's like, as long as this piece of code is computing some kind of IIS, we can attack this kind of piece of code. And it also enables some automation. And as an attacker, a lazy attacker, I really like automation. And we'll see, for example, by looking at tracing, an attack that has been introduced in 2015 by some names on the screen, that is called differential computation analysis. And this is like exactly the concept we exposed in the previous slide. It's like we have a classical attack on hardware implementation of IIS. It's called differential power analysis. We are going to trace the power of a chip and going to extract the key from the implementation. And here we can't trace the power of a Whitebox, but we can trace the execution and then transform this trace by serializing the bits in order to get something that looks like power analysis. And we can apply the same tools we had before in the hardware world in order to break our IIS implementation. So, and here we broke our Whitebox successfully. And this kind of attack don't require understanding the complex design here and don't require big reverse engineering. So the really nice thing today with DCA is like we started with this kind of empirical results, and now this has been completed by a lot of papers that brought mathematical foundation, generalization, optimization. And now we have many open source tools like side channel marvels and others to automate this kind of attack. And now that we automated this kind of attacks, we took this very hard to break kind of white boxes, and we brought it down to script kiddie level. Like let's download the tool and let's tweak the tool until it works. And it's very interesting from the attacking side. And there are like other kind of attacks we can do in a similar fashion. For example, we have fault injection. On IIS, we like to fault on the last rounds of the function statically by modifying the tables we have in the whitebox, or dynamically with some kind of instrumentation. And from that, we can recover the key. And today, like 5 years later, we have a lot of optimization and also a lot of tooling. And this kind of attack can be also automated blindly. And at the end of the day, it's like the same thing. Is like we open the gates to script kiddies because we have good tooling and good generic attacks, and we don't need to understand the underlying design. So here, like it's like midway conclusion on this building white box part, attacking and defense. When you use a white box, when you build one, you need to have some kind of ask yourself checklist. This ask yourself checklist has already in it, is my whitebox protected against code lifting? Is my whitebox data flow properly enforced? And now we have like per algorithm questions, like my IIS whitebox, is it protected against DCA? Is it protecting against DFA? And if you have several algorithms or several techniques you use in your box, often you need to have your own list. And so feel free to add your own items to this list, and feel free to inspire yourself from the standards, like having obfuscation or breaking the attacker's tools. And what you need to understand is like, if you don't protect explicitly against this kind of attacks, code lifting, data flow, DCA, DFA, your white box will likely be an easy break. And this is sad because we want strong white box. And now we are going to switch to another kind of algorithm, a more exotic one, ECDSA. ECDSA is a bit more exotic in the white box field because we don't find it in all white box. We talked about decrypting movies, maybe encrypting payloads, but why signing stuff in a white box? And here, this kind of algorithm we put into white boxes are often from the need of end-to-end white box. It's like the user don't pick the protocol, it's his implementing, and so the user need to protect his cryptographic implementation. And if the protection is like only on IIS, the rest of the protocol will be broken. So we often need end-to-end white boxes, and sometimes, especially in the banking industry, we get ECDSA sometimes inside. And how to build an ECDSA white box? It's a good question. You can try to take a look at the literature, but you see that few people publish designs, like no one, but there are still commercially available ones. So you don't know how to build a white box, but maybe you can know how to attack an ECDSA white box. You don't know how the design is made, but maybe by inspiring yourself from hardware attacks, without knowing how you can build an ECDSA white box, you can attack maybe the ECDSA white box. So we'll go into that after a small crash course on ECDSA. So ECDSA it's a signature algorithm. We have a message. We want to sign this message with a private key. And before doing the signature, we are going to pick a randomizer, a secret unique random key, and we are going to compute an exponentiation, an elliptic curve exponentiation kind of thing. There are like double and add and things inside, but we are not going into the details of the mathematics. Just know that there is this randomizer, and this randomizer needs to be secret and needs to be unique per message. And now we are going to compute the signature, and the signature is computed from the randomizer and the message. And at the end of the day, you publish the letter R, the result of the exponentiation and the signature. And we are not going into the details of the validation and everything else, because only knowing that this randomizer exists and that we need to compute signatures here, we can break ECDSA whiteboxes just by reading a bit of literature on ECDSA hardware attacks. And when I say literature, is often just open the Wikipedia page and you see that the textbook fault injection you can do on ECDSA is like shooting. What do I mean by shooting lasers? Is like from Wikipedia, you need a regular signature computed like with the real message. And you need another signature, a faulted signature with like a fault on the message. And the attack will enable you to extract the private key from these two signatures, these two public values, if and only if they use the same key and the same randomizer, but different messages like M and N prime. And here we can just stop, and before shooting laser, before attacking the white box, we can try to understand how someone building a white box will pick something at random, because the randomizer K is something that we picked at random, but maybe the people building the white box just open their view random, just read some entropy from the system and then picked K from that. So maybe you're the attacker, you control the hardware, you control the system. So maybe you will try to remove all the entropy. And now you will have your white box using the same randomizer for all the messages you give it to the white box. So you don't even need to perform a fault injection. Maybe it will work even before doing a fault injection, just by removing the entropy source. Let's close this parenthesis. And now we are going to move on porting this textbook fault injection that works on real hardware by shooting lasers. And now we are going to do the equivalent of shooting lasers onto white boxes. But what we can do onto white boxes is like we can clone the state of the application before computing the signatures. And then we can, from this clone, we can compute the signature once without a fault. And then we can compute tons of signatures just with while flipping bits somewhere. And then we are going to continue producing bit flipped signatures until we get a faulted signature, S prime, that enable us to perform the attack. And what we observe on the field is that this very basic attack, we got inspiration from the textbook hardware attack on ECDSA that we read from Wikipedia. But this kind of attacks already work on some commercially available white boxes. So what you can see here is like we still don't know how to build ECDSA white boxes, but we can still break some ECDSA white boxes. And on this topic, there is like another approach that we've seen is like doing tracing on white boxes. And here on ECDSA, it also works as an attack, because as we saw earlier, we have this K randomizer that must be kept secret. And now, what about doing some tracing? What about leaking K? And what you see is like often in the most naive implementation of ECDSA, we use for this exponentiation something called double and add. It's similar to square and multiply we do in RSA. And this kind of algorithm leaks K into the execution traces of the white box. And what we observe is like taking the classical countermeasure we see in the hardware world and applying them to the white box world. Often don't work out of the box because of the white box context. For example, windowing doesn't work because we can still do interesting tracing on the white box. And what you need to understand here is like often we have the same side channels as hardware implementation, but in a white box context. And in the white box context, these side channels are harder to mitigate. So at this point, we've seen how to attack the ECDSA white box. And now we may go into building this ECDSA whitebox, because you can build some, because you can have protection countermeasures against faults, against basic tracing that you can explicitly put. But instead of that, we are going to see kind of generic methodology, how to build a whitebox of anything. As we saw, we need to start by learning everything about attacks, doing faults onto an algorithm, doing tracing, also go read the literature about hardware attacks on this algorithm, classical attacks, but also if there is like whitebox literature on it, go eat the papers. And the second step is like asking yourself the question, is this algorithm a good idea to be put into a whitebox on the first place? Because not all algorithms are created equal. For example, ECDSA is easier to build a whitebox out of than RSA. But before that, you don't know, because there is like very little literature published on how to build this kind of exotic whiteboxes. And what you see is like you work with limited knowledge. You don't know about the ECDSA tricks before finding them, for example. You don't know about the RSA tricks before finding them. Maybe other vendors found out about these tricks. And maybe the attacker found out about these tricks, but maybe not. So in the competition between building the whitebox defenses and attacking, there is like, you must stay ahead. So you must pour a lot of research and development in it. You must have good whitebox foo, trickery. And at the end of the day, the attacker won't give you good feedback, like won't give you, okay, here, good tricks, but here you have a hole. So what you need to do, and it's the same conclusion as before, you need to care about protecting the thing that protects your secrets. You need to protect your whitebox against attackers with software protections, with things like that, because you work with limited knowledge, you're not perfect, your whitebox is a compromise. And if you want to get a good trade-off between performance and security, you need to be more creative than just doing mathematics. These kind of mathematics are a must-have to have good countermeasures, but these must also be mixed with software protections. So let's jump to the final conclusion. Whitebox cryptography, as we saw, there is like a lot of leaks. We have like attacks we can do on hardware that we can do on whiteboxes. And what we saw is like we need software protection. And today, we are not the only ones that made this kind of reflection. We have like 20 years of whiteboxes behind us. So today we have multiple industrial ready solutions. These are industrial ready to the point that they are starting to appear in global standards. For example, the banking industry has PCI POC. This is an interesting read if you want. There is like almost all the ask yourself checklist we had in this presentation. They have their own ask yourself, and it's very long and very interesting. And you must ask yourself the right questions. Often vendors will tell you like, trust us, but you need to say like, okay, what about code lifting? What about dataflow? What about DCA? What about DFA? Because if these whiteboxes are not protected explicitly, you need to find out, and you need to play this kind of cat and mouse game. You need to audit the whitebox. You need to have independent auditors specialized on the topic. You need to break your whitebox. You need to break the design you are building, and then you need to fix it, and then you need to repeat this loop. And now, whiteboxes work as a cryptographic protection, as a protection for cryptographic implementation. But there is also like hardware security. More and more we see in the mobile space, for example, secure elements and trustlets that provide hardware isolation for cryptographic operation. But this has often some fragmentation between devices. And what we observe in the real world is that these are often put behind closed doors for security reasons. And often when you are a small editor or a small bank or a small company, you can just access the secure element, or you can't just like have your own trustlet in the trust zone. So whiteboxes are still very helpful, and in both cases you need to protect the thing that protects your secrets. But if as soon as the secret data leave your whitebox, for example, or as soon as your movie leave your cryptographic component, the attacker is able to steal them. It's bad. So the overall conclusion of this presentation is like applications are best protected as a whole. Hardware security and whiteboxes are a part of application protection, but there is like many other parts on application protection. And yeah, it's not the topic of today's webinar, but this is the overall conclusion on building whiteboxes, attacks, and defenses. And now we'll switch to questions. I think we are going to have some into the Zoom chat, I guess.
Yes, there is one question from Shrayu. He wants to get into cryptography, and he has some pretty basic questions, not related to Whitebox crypto, but I think you or Philip would like to answer.
Okay. I'm still trying to figure out how I can access the question myself in the Zoom interface. Okay. Yes, I found out. There is like chat. Yeah, I have chat. So I am completely new towards cryptography and network security, interested in cryptography since quite a time. How should I start? What are the prerequisites I should consider? Can you suggest any free and up-to-date resources for beginner? How can I pursue cryptography as a career? Please guide me, sir. Okay, so I'm a junior in cryptography. I've just started my career in some ways. And there is like good books written by researchers. I can quote Introduction to Cryptography by Nigel Smart. This gives a good overview of all the basic things we do in cryptography. There is also the course that Dan Bonnet give on Coursera. There is like Crypto 1 and Crypto 2 given by Dan Bonnet that is quite famous. And these two are quite the basics you can do by yourself with resources on the internet. And then for the more specialized stuff and complicated stuff, I'll say is more like finding the good people to hack with, to practice, code, attack, implement. And it's a loop. Getting better from the basics you get by reading this kind of resources. So I guess good luck. I have not more things to add, but maybe my colleagues do. But yeah, I'm happy with my answer.
Anybody else has any questions to ask Matthieu? You can write down your question in the chat. But meanwhile, let me ask Matthieu one question. You mentioned there is PCI as a standard for Whitebox, right? Or they have a standard. Are there any industry bodies apart from PCI that have standards or recommendations for Whitebox crypto?
Not. Yeah.
Yeah. There's the EMVCo. It's in the bank payment industry, but EMVCo also has some audits they do on Whiteboxes, and they have criteria that they check, like things that Matthieu said in his presentation. So it's also one of the audit people, let's say, that starts to standardize the kind of things.
Okay. I have another question. I remember in some of the beginning slides, Matthieu, you mentioned that implementing Whitebox crypto could be expensive. So how does a small IoT manufacturer, what do they do? Have you seen small IoT manufacturers, OEMs using Whitebox crypto as a solution? Because
Okay.
it probably is expensive and they don't have a lot of budget for it.
Yeah, implementing from scratch a Whitebox is not easy in some ways, because often the ones that you will find published on the internet has been documented as broken by someone with a nice write-up how to break this kind of this Whitebox in particular. So often you need to start your own implementation, and you have good knowledge about the countermeasures and how to implement the Whitebox in the first place. And then you have a lot of issues to work out, like code lifting, dataflow, and these has good and bad solutions, but good solutions are mostly what are selling vendors, Whitebox vendors. So you can, if you are good at building your own Whitebox, you may consider like selling your own research and development, because not a lot of people know about building those and building good ones. But there is like, as a small, for example, IoT person building your own little product, you can find resources in the field in order, like when you are, for example, trying to buy a license, not just picking someone that will tell you like, this is secure. You can like ask yourself, is my code lifting problem fixed? In IoT is kind of different, because there are other things you can do, like having your own secure elements if you can spare the change. But yeah, you having the right words and the right question will enable you to not make basic mistakes. And often when you start thinking about your protocol, before making choices, if you want to have Whiteboxes, you can have other constraints that comes into play. So yeah, it's I don't have an exact answer to that, but yeah, come work with us, I guess. But
yeah, so
at the end of the day, yeah, it's not
manufacturers
easy to
go
roll
to
your own
Quarkslab for
cryptography.
sure. But I think you have one more question, Matthieu, in the chat. Can somebody find ECDSA Whitebox somewhere in order to test them? And are they public? Are there any public examples?
Personally, I'm not aware of public examples. We have samples, but we can't make them public. But maybe Adrien or Philippe will know about samples.
No, unfortunately, with many AS examples, but nothing asymmetric actually. Even RSA, I think there is no public example. Typically, you find this kind of stuff in CTFs, for example, or there was this Whitebox competition for IS Whitebox, but there is no competition yet for asymmetric crypto. Maybe it will come in years.
Yeah.
All right. I don't think we have any more questions. So thank you so much, Matthieu, Philip, and Adrian, for this amazing session. I'm sure Philip will come up with a CTF for this in the future. It's because there is nothing available. So yeah, guys, thank you so much for joining us today. If please share your feedback with us. I have shared the link, and if you're also interested to join our trainings, which are coming up in September, I've shared the link with you all. So thank you so much and stay safe. And Matthieu, please take care of your feet.
Maybe I can give my email or my company's mail, if people or if people have more questions. So like Yes. If you contact the generic contact link, people will forward your question to me, Adrien, or Philippe. So feel free to send a mail on contact@quarkslab.com. And if you have more questions, will the slide, can we make the slide available somewhere?
So I will, the webinar is recorded, right? So we'll be uploading the edited version on our YouTube channel, which is publicly available for everybody to view. So they will have the slides, they can see it. And also I'll mention your contact details over there if they want to contact you for any questions or any assistance or any guidance in the future.
Okay, so fantastic. Have a nice day, I guess.
Yeah. Thank you so much, everybody. Bye.